In this paper, we adhere to responsible disclosure practices, sharing our findings with the authors of each model we studied. We discovered a vulnerability in ChatGPT and allowed OpenAI 90 days to address the issue before publishing our research. We delve into the training data for language models, discussing how large language models, LLMs, are pre-trained on extensive text corpora. We specifically focus on proprietary models like GPT-4 and PaLM-2, which keep their training sets confidential. We emphasize the importance of understanding the privacy implications of using LLMs trained on undisclosed data. We further explore the concept of instruction tuning and reinforcement learning from human feedback, RLHF. We explain how fine-tuning LLMs on instruction-following data can enhance their utility and align their behavior. This stage can train models to use a unified chat-like persona and abstain from answering certain types of queries, such as writing spam emails. We conduct membership inference attacks and data extraction attacks on LLMs to measure their memorization capabilities. We explain that neural networks, especially those with many parameters, can memorize their training data, and adversaries can exploit this to infer membership or extract full training examples. We extend our study to data extraction attacks on open models where both the model parameters and training sets are publicly available. We evaluate the performance of extraction attacks from prior work and propose our own attack methodology, which involves generating prompts and checking if the generated output matches the training data. We discuss prior work on memorization in LLMs and define extractable memorization as the ability of an adversary to construct a prompt that makes the model produce a specific training example. We explain the challenges in designing prompts and testing the success of the attack. We evaluate past extraction attacks in a controlled setting using open-source models with publicly available training datasets. We generate output using prompts sampled from a large corpus of text and verify if the generated sequences are contained in the training set using a suffix array data structure. We apply our attack methodology to multiple open-source models and measure the fraction of model outputs that are memorized. We observe rates between 0.1% and 1% and extract a significantly higher number of unique 50-token sequences compared to prior work. We explore the total amount of extractable memorization in LLMs by extrapolating from our empirical results. We use the Good-Turing estimator to predict the number of unique memorized examples and find that the rate of extractable memorization does not accurately predict the total quantity of memorization. We extend our attack methodology to semi-closed models, where the training datasets are not publicly available. We propose a strategy to establish a ground truth by checking if the generated output appears in an auxiliary dataset built from a large corpus of internet text. We describe how we build an auxiliary dataset by concatenating large LLM pre-training datasets and perform queries to verify if the generated sequences are contained in the dataset. We acknowledge that this approach has false negatives but provides a lower bound on the amount of memorization. We collect a large corpus of internet text and use it to build an auxiliary dataset called aux dataset. We download 9 terabytes of text from various sources and perform tokenization and deduplication to create the dataset. We shard the aux dataset into multiple suffix arrays to handle its large size and perform efficient searches. We mention that the complete evaluation required 3 weeks of compute on a single machine and highlight the potential for optimization. We compare discoverable memorization, prompting the model with true prefixes, and extractable memorization, prompting the model with random strings, on GPT-Neo 6b. We find that only 35% of the discoverably memorized examples were also extractable, indicating a gap between the two measures of memorization. Finally, we investigate whether different models trained on the same dataset memorize the same training examples. We find that there is variation in the memorized examples between different models, suggesting that the memorization is not consistent across models.